Thank you for the introduction, and I appreciate your kind invitation to present this talk in your chapter, and I hope it's going to be interesting for the attendance. So please feel free to ask me questions during the talk, and like any questions and any time. So my talk is on full waveform inversion of fiber optic VSP data from deviated wells. So this is a joint work which actually several divisions participated. So we have Schlumberger and client, two clients, and actually inside Schlumberger, this is a collaboration between like research, engineering, and operations. So this is the outline of my talk. So I start with the introduction for DAS and borehole seismic data. Then I move to a general description of the algorithm, and later I will give a little bit more technical details on its 2D implementation. And I show two real data application, and I will end up with the conclusions. So I decided to give actually quite a basic introduction for the borehole seismic. So my intention was so why I tried to do that, because I think the SPWL community is not like some people can be not familiar with that. So this is just a very general, very basic overview. So when we talk about seismic, people typically think about surface seismic. And in surface seismic, we have all sources and receivers on the ground, on the surface. And when we talk about for the borehole seismic, we have receivers under the ground, so in borehole. And sources can be either on the surface, and such acquisitions are called VSP, or vertical seismic profiling, or the sources can be in the nearby well, and such acquisitions are called cross-well seismic. So this talk is going to be showing examples actually for borehole seismics. But the whole techniques and actually are applicable, and we are working on that, applicable for cross-well seismic applications, and also for surface seismic in general, but there are some specifics which are related to the borehole seismic. So for VSPs, so these sources are actually typical seismic sources located on the surface, and depending on the depending on how many sources we use, how they are positioned, we distinguish several borehole seismic acquisitions. For example, zero offset VSPs, where we have a single source close to the borehole, or an offset VSP where we also have a single source but a little bit away from the borehole. There can be multi-offsets VSPs, so there can be walkaways when we have a number of sources aligned approximately in a single, in a line. We can have walk above, which actually is similar to walkaways, but for deviated wells, it's the special name in case of deviated wells. And we can have a general 3D VSPs where the sources are covering the area around the borehole. So the goal of this different acquisition is just like different acquisitions are trying to achieve different objectives, and like depending on the objectives on the target of the surveys, one or other acquisitions can be used. So actually, why VSPs are used, why surface seismic is not enough? There are several reasons. Actually, when we are talking about borehole seismic, we already have a certain knowledge about the subsurface. So we have at least a well there. So we do have already a certain information about the formation, which comes from the well measurements and maybe surface seismic. And the goal of the borehole seismic acquisition is to is to like get more precise, more specific information about the target. And one of the goal is to get a high resolution. So why it is why we can achieve it? So first, for VSPs, either we use the same source as for surface seismic, but the waves are attenuated less because they propagated through the shallow surface, which attenuate waves the most only once. And the frequencies of the signal which we have in body hole are higher. And also in VSP service, we have a lot of shear events, and which has a smaller wavelengths and which gives us a higher spatial resolution. And for crosswell seismic, actually, the different types of source are using, and they have a high frequencies, which can be a few hundred hertz or even above 1 kilohertz, depending on the source type. So the first goal of body hole seismic is to get a high resolution, but also because we have a very a lot of events measured in the body hole. The data are rich on the events. We have direct compressional, we may have direct shear for certain cases. We have PP reflection, PS reflection, SP, like a lot of can have guided modes, can have head waves. So actually the data are quite rich, and we can get not just information about reflectivity of compressional velocities. We can also have information about shear velocity and about anisotropy. And this all allows us to better characterize the subdomain, better characterize the target. And this is another goal why body hole seismic surveys are done. So for decades, the body hole seismic data were required with the hydrophones, and also for geophones, which gives much better signal-to-noise ratio. But in recent years, more and more VSPs are required with distributed acoustic sensing, or DAS. And so I would like to give a very simple example of try to give you an understanding of what type of waves do we measure in body hole seismic data. So let's say we have a vertical well with several receivers, and we have source, here it's, let's say, vibrator, which injects a seismic wave. So this seismic waves propagates, and we measure a direct wave in the receivers, which goes like that. Also, this wave can reflect from some deep interface and come back as an upgoing event, and we measure it here. This wave can be bouncing back and forth between a certain shallow interface and the surface, or another shallow interface, and come back as a downgoing multiple like that. Or we can have this multiple going deep into the subsurface and then bouncing back and measure it in the receivers as an upgoing wave, which is like upgoing multiple. And even for this very simple example, this is not the whole events. You might imagine that there can be a lot of multiples here. But for the real case, when you have a lot of interfaces and when you have P to shear conversion, you have all of these complex events in the receivers. And all of these events and the attributes are like travel time, the polarization, the amplitude phase, they actually accumulate information about the subsurface properties, which we would like to use to extract the medium properties as itself. And full waveform inversion technique, it's very popular in seismic in the recent decades, even more. It, in theory, allows to use all types of events, and while a model it solving partial differential equations, meaning that we try to model realistic physics as close as possible. So I'm not gonna give the deep introduction about fiber optic measurements, so because it should be like a different talk, but in simple way. So distributed acoustic sensing, or DAS. This is a technology which allows you to measure strain of the fiber caused by the arrival of seismic waves. So you basically have a controlled source injecting seismic waves, which propagates through the subsurface, reach the fiber stretch, and this stretching you can the strain of caused by that stretching can be measured. So this sensors become very, very popular because it allows to, it's an alternative to the conventional GFON array, but it allows a much faster acquisition. So you don't need to deploy tool in the well. So and like move it, and so it's significantly faster. It also gives the full coverage of the well and dense sampling. And originally, when this fiber optics was introduced, the data quality was not comparable with geophones, but in the recent years, because of the improvement of the hardware and the deployment, like the quality of DAS data significantly improved, and they are in some cases they're even comparable to the geophone, so not too far from it. So how can we use DAS benefits, meaning that it's fast and it gives us actually quite rich data similar to geophones in the processing? So first, we need to create the algorithm for which works specifically for this DAS, this fiber data. So while they're similar to geophones, they're not exactly the same, and this needs to be accounted in the algorithm. And so we would like also to use the richness of the data, meaning that extended illumination, dense receivers, and use as much ones as possible because it allows us to give a better medium properties, and we want the method to be reasonably fast. And all of that we try to achieve with elastic full waveform inversion, and we formulate it for average strain measurements, which is related to DAS. And of course, just because of the full waveform inversion nature, so we invert for all or as much events as we want or can. Here I want to present the formulation directly for DAS, and we actually construct the algorithm, implement the algorithm for 2D acquisition, which is quite fast. Okay, and let's go to the algorithm. So first, what is full waveform inversion in general? So we actually have an input, which is data, which is initial model and any prior information which we would like to use. And then we actually would like to invert the data, meaning that we would like to feed the observed data with the synthetic data. And this synthetic data, they depend on the model parameters, meaning medium properties, and they can also depend on a certain parameters of the source. So while it's a controlled source, but we sometimes don't know accurately enough at certain characteristics of that. So we would like to fit it, and while model synthetic data, we solve partial differential equations of the wave propagation. The technique is based on construction of the gradient of the cost function. So cost function, so here I use a simple weighted list square norm. So actually other formulations are possible and used. And so the gradient is computed by the joint method, which is a key component. And this method allows us to efficiently compute the gradient. Then based on the gradient, we compute a model update, and we update the model, and we go with iteratively, because this is a non-linear problem. So the dependence on medium parameters, data on the medium parameters are not linear. And at the end, we have, in our case, compressional shear velocities, anisotropy, and actually bulk density here as well. So for surface seismic, FWI is now used a lot for commercial jobs. For borehole seismic, so it is used, but it's not as like a common and well-established procedures. But there are several groups who have results and published on that. So one of it is our group. So we actually have processed a number of VSP data sets for conventional geophones. So some of this work are published, and I showed here like a few examples of that. And for fiber data for DAS, there are also several groups with results. So one is our group, and so we actually work with the FWI formulated for DAS measurements directly. And what I'm going to present right now is like more detailed description of the algorithm which we presented in 2017 and partly in a brief way in 2021. So, but there are also a group in the Australia and the Curtin University who applied FWI formulated for velocities to DAS data. So, and have results, and also a group in Calgary University who are working for DAS measurements as well, and they work with straight and shaped cables. And just I want to note that the work I'm going to describe later is only for straight cable. So what is our goal? What was our goal originally was to formulate FWI, elastic FWI for DAS, and show, like make a feasibility study, just confirm how it's working, what can be the issues, and like learn on what we, how can we improve it further. So I have a few slides with formulas. So if you are not familiar with some of that, just don't worry. I just want to give some specifics, but I try to describe it in a simple way, and I avoid some technical details so they can be found or derived by the interested listener. So we work with the elastic wave equation. So here is the elastic wave equation. So we have a displacement field here, stress and strains, and our model is in these two parameters. So we have a density and we have a stiffness tensor, which depends on compressional shear velocities, density, and also anisotropy parameters. And we have a source terms, which is F and G. They split it just to have a maybe more convenient notation for seismic people. So we model DAS as a strain, as an average strain along the valve. So it means that actually we do not account for borehole effects, and we assume a good enough coupling of the fiber with the formation. So that basically we associate the strain in the fiber with the strain in the formation, which is not exactly the same thing and depends on the coupling. So all of the what is described later does not take account on the inaccuracies or not perfect coupling. I will say a few words how can we try to compensate for that. So DAS in a certain point is modeled as a strain along the well, which is maybe actually not exactly the same as the fiber, but close enough, and average along the well. And for the averaging, we use a gauge length which was used in the operations on the job. So in the vector form, so we just write this equation in the vector form. So we have a vector of point strain measurements along the well, and the averaging matrix on the top of it. And actually by this formula, like clearly show that the data are spatially correlated. And the key component of the FWI is the computation of the gradient. by joint methods. So what a joint here, what a joint is. So we have a gradient of the cost function versus model parameters. And in simple words, it is a cross correlation of the forward propagated field and backward propagated residuals. For elastic, there are some like derivatives involved. So, but let's say don't pay attention. This is just forward propagated in U, field U, cross-correlated in time with the backward propagated field W, and this is done for all special points of the domain. So forward propagated field is injected from the source, and this is the source which was used in the field, and propagated to the receivers. For the source, we have a for the right-hand side, we have the injection of the physical source. Backward propagated field is injected in the receivers. The wave field which we inject is the residuals between the observed data and data modeled in the forward propagated step. So we inject these residuals and we inject it with a certain radiation pattern, which I'm going to talk later, and that's it. So what is the difference? So if you go through the all mathematical formulation, all math formulas, what would be the difference between geophones data and DAS data? We measure it as like assuming that this is averaged strain. So for geophones data, the residuals are injected as the force term. But for the DAS, for the average strain, first the residuals are averaged in space and then injected as a moment tensor source. And the radiation pattern of this moment tensor source, which is actually like described as a matrix here, it depends on the deviation of the cable. So basically you have a deviation of the well, and based on that you construct the moment tensor, which would be applied for the back propagating of the residuals. So what I actually want to say by that is that if you have FWI formulated for conventional measurements, this is not a big deal at all to change it to strain measurements. So it requires just a modification of the backward propagated source radiation pattern, and that's it. Let me let's say say a few words like why we are using a few words about that. So actually in borehole data we need to use elastic wave equation, and why I'm emphasizing on that actually it's like a certain very important detail that distinguish the surface seismic from borehole seismic. So in surface seismic, even till now, a lot of FWI applications are done using acoustic codes, meaning modeling only compressional waves. And this is justified because in a lot of cases, it's not so much importance of modeling shear. There are like more work appears on the elastic FWI for surface seismic as well, but for borehole we just need to use elastic because we have a lot of like shear events which we need to account, otherwise we would not get a good result. So, and let me go to the 2D algorithm implementation. So actually, why we are talking about 2D? Of course, it's because of the cost, the computational cost of the computation. So FWI is quite expensive, so you need to model numerous forward modeling and then joint computations for like a lot of sources, and this is quite heavy jobs for 3D elastic. So 2D is much computationally affordable, but also there are one more reason, and this is because of the acquisitions type used in body hole seismic. So in a lot of cases, we have just like walkaways or multi-offset VSP jobs done. And in this acquisition, we just don't have enough resolution in the whole 3D space. So we can we have sensitivity around the acquisition plane, but we couldn't resolve far away from it. So anyway, we need to use an assumption about anyway we need to use a certain 2D assumptions. So the common way to do it is assume laterally invariant dependence on the medium properties. So perpendicular to the acquisition plane, the medium properties are assumed to be invariant. But here we use actual symmetric approximation, which is actually used a lot in global seismology. In actual symmetric approximation, we actually work with cylindrical coordinate systems, so radial, azimuthal, and vertical, but assume that medium properties do not depend on the azimuthal direction. So this allows us to actually reduce to work with the partial differential equation in two coordinates, r and z, so with almost the similar computational cost as to the Cartesian algorithm, but it allows us to model 3D point source, a realistic one, and also it allows us to model out of plane deviation effects of the acquisition. So because in reality, there are certain out of plane effects. If you we go through the all mathematical formulation, derived formula specifically for this case, and actually this is the formulas for strain, and also it can be considered as the formulation for the moment tensor for the backward propagated field. And we have an azimuthal term here, which actually corresponds to the non-out of plane effects, and I will show later that it's important. And of course, this joint is not the only thing that you need to do in FWI. So there are a lot of other steps and in the workflows which need to be done to obtain a good results. So I here listed some of them. So one of the question is how to work with the source wavelets, and in our based on our experience, so for land data we invert for the source wavelet and starting with the theoretical sweep for the initial wavelet construction. But for marine case, so when you, and we do it for land because the source wavelet for land is not consistent with the short position, and it happens because of the difference in the ground conditions, different coupling of the vibrator, different shallow medium properties. So the signal which you get from one shot to another can be quite different. But for the marine case, where we use an air gun, the wave signature is quite consistent between the shots, and we do not invert for it. So we invert for its amplitude, but not for the shape. And as a starting point, we use a far field measurements for the same or very similar air gun in a similar condition, which is used on the field. So we also need to think about how we adjust our real measurements and math formulation, because in reality you can have like strain, velocities or accelerations. You can have measurements of the source wavelet in a certain unit. So how to put it how to put everything of that into the same math formulation and have it done in a consistent way. And also one of the key component is constraints that you inject into the algorithm and workflow. So there are so we implement it as weights in the data model and source wavelet space, and the simplest one are described as a mute part of the data, constrain the model parameters to be like on the same scaling, use smoothing, use correlation between them, and also you need to think how about the workflow steps, like what maybe you would like to invert for a certain types of event first and then include the other events. So it can be like quite elaborate. And the implementation which we use is using spectral element methods for the wave equation discretization. And it is implemented on a GPU, which also quite efficient. So the computational time on the modern GPU cards are like quite affordable. So let's go to the real data examples. So the first example is a multi-offset VSP. This is from Canada and done in collaboration with Velvet Energy. So we have a well here, so it starts at the vertical, but around 700 meters deep, it deviates and then become vertical again, close to vertical. We have a fiber, not till the top, but till some distance. And at the bottom, below the point where we have fiber data, we have a regular geoforms. So this acquisition is not typical at all, because actually the source line was not aligned with the well deviation. So this is not typically how it is done. It's almost perpendicular. So it was done by certain technical reasons, because it was a test and they had the operation had a very limited time to make the job. So they just showed how it was more convenient. And it's not like a real walker weights, because in like real walker weights there are maybe more shots than it's here. So the fiber is deployed in the well, and the coupling of the fiber is assumed to be quite good on the deviated part. So because of the gravity, so gravity just make it job, and we don't need to do anything in addition. But in the most vertical part, it's in the vertical part of the well, it's a challenge to maintain the coupling of the fiber with the well bore, and here the magnets was used in a certain areas. So the data were actually quite a good quality here. So because of this strange acquisition, so we did not even invert for 2D profile here. We invert for 1D because we don't have enough information from the data to resolve to obtain that 2D answer for the deviated part of the well. So so we go to quite low frequencies here, up to maybe 30 Hertz, and this is the results for the inversion of only fiber part of the data. So you have real data here, and you have here this is an example of how it is reconstructed by FWI. So direct waves, like reflections, conversions, so they're all presented in the synthetic data as well. And this is the comparison of the result with, it's not actually sonic data, but this is data, this is the model based on sonic. So sonic data had certain issues with this well. So this black is a reference model, which is constructed based on sonic and VSP travel times. Green is initial model which we started with, and blue is the model reconstructed by FWI for compressional and for shear velocities. So for this type of, for this level, for this values of frequency, this is a reasonably good fit. And so we did one more like experiment here. So we actually tried to estimate how out of plane well deviation effect are important. So, and here we did a modeling of on the FWI model, but avoiding this is the Mussel term. which accounts for the azimuthal effects. And we got this wave field. So actually all events are the same, but the amplitudes differs, and they differs in this deviated part. And if we try to invert without this azimuthal term, then we tried to do that and we get not a so good result. So meaning this out of the deviation effects in the fiber should be taken into account. And this is the result of the application for fiber and conventional geophones. So top is fiber, bottom is conventional geophones, and again we had a quite good results. You can see here a certain like issues which requires proper treatment, and this is the amplitude of these reflected events. So they're not the same, and we suspect that it happens because we don't perfectly know the scaling between units of fiber data and geophones. So we have a certain estimation, but it's maybe not accurate enough. And for the future, the best way would be actually to include this scaling factor into the inversion. And we think that it will allow to adjust the amplitude much better. Okay. Next example is marine in the Mediterranean Sea, done jointly with ENI. So here is a deviated well, almost in the same plane, and here the acquisition was like walkaway, like line for the sources are close to the deviation plane of the well. So there were several shots. It's not, again, not a real walkaway. This is multi offset VSP, and we invert 6 of them, avoiding the closest to the wellhead. So because it's like more away from the acquisition plane, and so one of the feature here is actually the changing. You can clearly see the change. So this is the real data. You can clearly see the change in the amplitude in the data. And this actually happened because of the difference in the coupling conditions. And we corrected for it empirically. And actually, for the future, it might be better to invert for this scaling factor, which would account for the different coupling properties. So this job was actually a little bit more challenging because we did not have a good initial model here, neither for compressional and actually no estimation for shear. And we adjusted the workflow a lot to account for that. But and it actually worked. And the best way to construct initial model was to use a certain empirical relation between compressional and shear for the initial model. So we tried several and like choose the best one. And I talked about richness of the body hole data. Here I maybe would like to have to give a little bit more detail. So this is actually the real data and FWI reconstructed on up to 60 Hertz. So we have a direct P, we have a conversion to shear, we have a multiple here. It's a C surface, C bottom multiple. Another one is coming later and later. We have compressional and shear reflection on a different depth. We also have here the effect of so-called air gun bubble. So the signature of the air gun source is like it has a very compact signal broadband in the beginning, but then later lower amplitude, lower frequency signal, which is called bubble, is coming, and you can see it in the real data. And actually we have it in synthetics by properly modeling using the proper wavelet for the air gun. And inversion reconstructed like all of these events quite consistently and with a good accuracy. So I have it's not like a real movie, so but I have a model reconstructed by Inversion here. It is not changing, but the shots, the source position are changing, and you can see how the wave field is changing from one source position to the other, and how Inversion is reconstructing it. So it goes by cycle. Okay, so let me conclude. So we work with the borehole seismic data, DAS or fiber optic measurements, and we suggest and actually try to validate here the elastic full waveform inversion formulated directly for strain measurements. So we have we don't account properly for the non-borehole effects and assume a perfect coupling, and this is the point which might be probably improved further, but it actually, this formulation allows us to automatically account for fiber directivity for different wave types, automatically account for gauge length, gauge averaging. We do not need any conversion of fiber data to velocities. And using this algorithm, we can simultaneously invert fiber data with conventional measurements. So the implementation for 2D acquisitions accounts for the 3D well deviation effect and actually have a quite modest computational cost. And we showed that it successfully worked for real data. Okay, so I would like to thank our clients to allow to present this data and the whole acquisition team who participate in the acquisition and the data processing. And I thank you all for attention. Any questions?
Thank you, Olga, for the interesting presentation. We have all audience here in person and also a couple of people online. Mm-hmm. So please let me know if any of you have any questions. Domenico, yeah, go ahead.
Hi, Olga. Thank you for the talk. I have a couple of questions. So the first one is, which is the uncertainty of your result comparing with the real data that you have?
Could you repeat? There is some echo.
Yeah, he is asking about the uncertainty of your model, right?
About what?
Uncertainty.
Uncertainty. The algorithm. So this like a formulation. It does not give you uncertainty. Like you can actually speak about the following. So first, not the whole region. You don't have a resolution in the whole region. So what might be done is an estimation of the illumination of the coverage, and this can be estimated, but this is not like done here. And uncertainty, there is no like an uncertainty number associated with like each special point.
Yeah. What I meant more was because before about when you compare the sonic construction with the result of the inversion, I think it's the previous case, the land case.
Mm-hmm.
But also there's another question about, yeah, you can go back here. Like you can see that the blue curve and the reference curve, they do not overlap like all the time, right? So there is a good match, but in some point, in some depth, there is not a good match between the two curves. So I was wondering, what is in your view the reason of it?
So first, you could not expect, for example, to coincide because there are different frequencies. So the best you can get is that the upscaled sonic should be in agreement with the seismic. And yes, so this is like a valid question. And what I can actually tell you, so when we go to the higher frequencies, for example, here, there is also comparison with sonic. So this is higher frequencies and this is geophones. And the correspondence with sonic, so this is shear, is like quite good. But this is high frequencies, like more than twice that we do have in this fiber example. So there are there is a confirmation that actually if we if we go to high frequencies, the agreement with sonic increase. There are again a certain can be a certain certain discrepancies, but I think we are not on the stage to say that we can like quantify it and say what is correct one. I think in a lot of cases there should be a certain investigation of what is going on. But yeah, we would trust sonic and the effects of not like fully matching them. Here I would say it's attributed to the low frequencies and maybe to a certain not maybe perfect fit of the certain events. So. And just comments for the case here, because it's not like exactly sonic. This is a reference model, but it's not maybe as trustful as the real sonic.
Thank you.
Mm-hmm.
Any more questions?
I have one question.
Yeah, another question here.
Thank you for your presentation. And my question is, so you can you apply the
Can you hear me?
Yes, the quality is not good, but yes, I can hear.
Okay, so you apply the SPWI method to the DOS data, so it's a very good technical stuff. And so my question is, if you can run the acoustic logging to get P wave and S wave velocity, but why you use this technique to get P and S wave velocity?
Okay, let me maybe come back. Let me try to answer, and then you comment, am I answering your question or not? So because sonic will give you resolution just at the well, yeah? Mm-hmm. But what you would like to get from seismic is the properties away from the well. Mm-hmm. Okay. Yeah, and how far can we resolve? But we would like to have it as far from the well as possible, but with the highest vertical resolution as possible. So you will get a seismic resolution in vertical direction, which for FWI VSP high frequencies can be like even less than 10 meters. So it's much better than surface seismic. But of course, it's not the same as in sonic. But you got these properties like away from the well. How far you can resolve, it depends on your case. So how far are your sources? What is exactly the formation? But let's say for a general number, let's say we have a few hundred meters, like 300-400 meters, half kilometer away from the well. So this is how far we resolve. So if we would like to know a certain how the certain horizon and maybe properties in a certain layer changes away from the well, or maybe some feature away. So sonic data could not give you this, but seismic can.
Okay, so the last question is so there is a very important application about the VSP, that is detect the fracture around the ball hole. So I didn't say in this presentation, I didn't say any case of related to this. So did you have a very did you do some project like when you apply the DOS data to detect the fracture, it has high resolution?
No, I don't. Yeah, I understand what you're talking about. No, I don't have such example to show. Okay. So potentially, I mean, this would be like, this is very interesting to try, but no, not here.
Okay. Okay.
No.
Mm-hmm. Okay, thank you.
So we have time for one more question. Anybody from the online audience would like to ask a question?
Yes. Yes, I'd like to ask a question if I can. This is Carlos Torres Verdin. Thank you so much for an excellent presentation. You mentioned several things. So you're assuming proper coupling of the cable with the casing, I suppose.
Yes.
And also, when you design the cable, you're assuming a certain separation between stations. Plus, before you do the acquisition, you already know how to interrogate the cable, which is obviously in the low frequency band of the system, correct?
Yeah.
Now,
yeah. So yes. So we assume like a perfect, like a good coupling, and because we would like to work with the quantities that we can obtain solving elastic wave equation.
Yeah.
And actually, originally, that was the main concern of how good is this coupling, how good would be the amplitudes. Yeah, even like when we see a good quality data, meaning we see reflections and a lot of like reflections and conversion in the data, there was still a concern originally that how accurate they are to apply this technique. First, like maybe a comment that FWI can be formulated in a way that it would be less dependent on the amplitude. But this was not what was done here. The second, actually, by trying to invert this as it is, we actually got a quite decent result. I'm not saying that it's perfect, but it gives a confirmation that the amplitude is not so bad, and can be used in a data of a good quality. And also, what we have in mind to work on is introducing a certain, let's say, transfer function for the receiver side, meaning that would be like in a simplest way, it can be just a scaling factor at a certain depth position to try to compensate for the variations of the amplitude, maybe due to not perfect coupling.
Okay, so technically you are doing some calibration, right?
I would say here I did a calibration just empirically and accounting for the visible difference in for example, like here, so you see in a visible way, and I did empirical adjustment of that. But like I think so. I'm not presenting it right now, but the way that I would try to address it is to introduce a calibration inside the inversion, like try to invert for these calibration parameters.
Yeah.
And your second question about like discretized data. So what we actually get from the field up after optical data processing is discrete values of the strain or strain rate, but they are like averaged along a certain length around, like along the cable, and this is what we mimic here. We actually compute the strain in a certain, let's say, dense grid, and then average it.
Yeah. Yeah. So okay. So that's a good point.
We work with discrete measurements. Yeah, but we try to account for this averaging by like averaging of the strain, and this is close like what is done in the field.
Yeah. So this is like applying a low pass filter to the data.
Yeah, kind of. Yeah.
And
yeah.
And of course, you could apply. I mean, you can play also with the length of the array that you're.
Yes. Like theoretically, I may be even trying to invert for the best one to use. Yeah.
Exactly. Now, the second point is obviously you mentioned, but very quickly, that you use the first part of the data to estimate the wavelet.
Yeah.
And
let's say you should distinguish clearly between land case and marine case.
Yes.
Because for marine case, let's say there are available, or you can simulate it using a certain software. These wavelets, they depend on the air gun configuration, because it's typically like an air gun array in certain distance. There are software which allows to simulate it, and there are far field measurements which measure this field. And I worked with like a number of marine cases, and I found that in all cases it worked reasonably well. No big issues. You need if you don't know the units either for these measurements or for the data, what is need to be done is inversion of the amplitude, which is based on the first arrivals.
Yeah, that's what I was going to say, that the estimation of the wavelet by itself is an inverse problem.
Yes, yes. So how it is done, let me there is like there are several techniques which are published how to do it. So you can actually combine in certain way, and in some cases we play with what we exactly apply. So actually this problem of the source estimation is not like nonlinear as for medium. You can, for example, first invert for the wavelet, and then for the medium, and maybe do it iteratively, or which works actually not bad for a lot of cases, try to invert it simultaneously, but using a certain scaling between the gradients, which also work in a certain ways. And like you may not use the whole field to estimate for the source wavelet, and use a certain window.
No, that's okay. But so it's okay. That I understand how you're doing it. But are you neglecting multiples in the data?
No, multiples are included
in the inversion. And also,
but it's included. Each step of the inversion, each iteration is like linear, but the whole iterative procedure gives a non-linear. So here, for example, this is simple multiple. Is actually it's in the initial model. So you have a fluid path, and you have sea bottom, sea surface, and this is kind of in the initial model. But now we have a lot of examples where we estimated the multiples, interbed ones, quite good.
Okay. Obviously, I mean, you could have done standard low frequency model to invert for the low frequency velocity model, and then do migration that is typically done in seismic acquisition. If you were to compare the DAS results after full waveform inversion with the standard technique of using, how would that comparison be?
So we did it recently for Crosswell. I can answer for you for Crosswell.
Okay.
I don't have exact and maybe we will present this work quite soon. And for the Crosswell, we had this, let's say, we compared different migration results based on FWI model, but this actually was not like super low frequency model. It was a relatively like high frequencies, maybe smoothed a little bit to make migration works, and different types of migration. And we see and what we compare is actually you can compute in recent years, like a lot of people, what they do is compute an image based on FWI result. Yeah. And how they do it, they basically, if you have a certain structure, you like differentiate, convolve perpendicular to this structure to extract the discontinuities. And we compared these images, and the FWI images, and it actually was shown there are publications for surface seismic as well, that these FWI images are superior to migration images.
Okay.
And we do have confirmation on it for Crosswell. I couldn't show it like here. Yeah.
Obviously, you could also apply travel time tomography, right, for the analysis.
Yeah. But the original goal for polyhole seismic was to go to high frequencies, not to limit not to limit the because this is elastic data, and when you do this elastic migration, like migration for elastic data, yes, there are like you separate P, she, and then you have different images, and yeah, we like from the beginning we targeted high frequencies for body hole seismic.
Sounds good. Thank you. Thank you so much.
Thank you. Thank you for the questions.
Thank you, Olga. I think we already thanked you. Thanks for attending and accepting our invitation. Thanks for that interesting talk. Do you have any recommendations, any questions, any comments?
From my side, yeah, thank you for the invitation. So I would love to come in person, but that's not easy nowadays. Yeah, thank you.
Yeah, I would love to have you maybe next year or something in person.
Yeah, thank you.